8.2 Try It Yourself 1. The braking distances in feet of two cars were tested when traveling on wet pavement at 60 miles per hour. The results are shown in the table. Can you conclude that the mean braking distances are different? Use alpha equals 0.05. Assume the populations are normally distributed and the population variances are not equal. For this one, we have small samples because our sample sizes are less than 30 and the population variances are not equal. That's going to make a lot of difference in the formula that we use. First, let's set null and alternate hypothesis and find our claim. So we're going to ask us if we conclude that the mean braking distances are different. And so that's going to be equal to and not equal to. So our null hypothesis has to be the equality, so that's going to be equal to mu sub 1 is equal to mu sub 2. And for the alternate hypothesis, we're going to have mu sub 1 is not equal to mu sub 2. And this isn't really the claim, it's just asking you that. But that's the difference. That's if we wanted the difference. And so that's kind of our claim there. And so what we're going to do first is notice that this is going to be a two-tail test. This is two-tail. Let's find our critical values. So we've got a two-tail test. And we need to use our table. We're going to use table 5. Now our degree of freedom here is for the small samples. If the variances are not equal, then the degree of freedom is going to be the smaller n minus 1. The smaller. So our smaller n is going to be 8. So that's going to be 8 minus 1 is equal to 7. It depends on whether the variances or standard deviations are equal or not equal. So we're going to get a degree of freedom of 7, and our alpha here is 0.05, and it's two-tail. So we've got two-tail, alpha is 0.05, and our degree of freedom is 7, so that's going to give us 2.365, plus or minus. So 2.365 on the left-hand side, and 2.365 on the right-hand side. Now let's find our z. So the formula for our z here is going to be x bar 1 minus x bar 2 divided by the square root of, and it's going to be the same as pretty much the large sample. It's just s1 squared over n1 plus s2 squared over n2. The big denominator comes about when we have that they are equal. So in this case, we're just going to use the 141 minus 151 divided by the square root of 7.0, which is 7 squared divided by 8, plus 3.1 squared divided by 10. So let's put that in our calculator here. 141 minus 151, and then we're going to divide that by the square root of 7 squared divided by 8 plus 3.1 squared divided by 10. So our t is going to be, it's actually t, not z, isn't it? Negative 3.7, we're going to round off to 7.6. Negative 3.76. So if we put that in our thing here, negative 3.76, that is in the critical region. Therefore, we reject the null hypothesis. And the question was it different? So since we reject the null, we're going to accept the alternate. There is a difference in the mean braking distances of the two vehicles. 8.2 Try It Yourself 2. Manufacturer claims that the wattage usage of its 17-inch flat panel monitors is less than that of its leading competitor. You perform a study and obtain the results shown at the table. At alpha equals 0.10, is there enough evidence to support the manufacturer's claim? Assume the populations are normally distributed and the population variances are equal. That's going to make a lot of difference there, that the variances are equal in the type of formula you use. So here we want to know if it's less than. So less than is going to be an alternate hypothesis, so we're going to have mu1 is less than mu2, and that's going to be the claim. And we know that it's less than because the manufacturer says that they're less than. So alternate hypothesis is going to be opposite, which is greater than or equal to mu sub 2. So let's go ahead and make our curve here, and we know that it's going to be a left tail because of our less than here in the alternate hypothesis. You go by the alternate hypothesis. And we also know that the alpha is 0.10. Now we need to know the degree of freedom. Now to figure out which degree of freedom it is, when the samples are small here because they're less than 30, the variances are equal. So if the variances are equal, then we're using both the n1 and n2. The degree of freedom is n1 plus N2 minus 2. So in this case, it's going to be 12 plus 15 minus 2, which will give us 25. So we're going to look up alpha is 0.10, a one-tailed test, it's going to be negative, and the degree of freedom is 25. One tail, alpha is 0.10, degree of freedom is 25, that's going to give us 1.316 for our critical value, negative 1.316. The next thing we need to do is we need to find our t formula. In this case, our t formula is going to be the big one, and that's because the variances are equal. So the numerator is going to be the same, it's just going to be x bar 1 minus x bar 2, and you know that mu1 minus mu2 is equal to 0, over this big long thing I'm going to come up with here. It's going to be the square root of, and we're going to put a parentheses in front of that square root when we put it in our calculator. The square root of, and we're going to put a few parentheses here also, n1 minus 1 times the standard deviation squared. So if they give you the variance, you know you're going to have to not square it. But if they give you the standard deviation, you are squaring it. Plus, and then we're going to do n2 minus 1 times the standard deviation of the second sample squared. We're going to close that parentheses there. So there's our first set here. Our second set is the numerator here. And then our third set is going to be the whole square root. And then it's going to be parentheses n1 plus n2 minus 2, or you can just plug in that 25. And then our next set of parentheses is going to be the one that usually in your calculator it's already going to have it. We're going to put that in a second set of parentheses. And now we're still in the denominator. We're going to multiply by the square root of, and we're going to have parentheses, 1 over n1 plus 1 over n2, close parentheses, and then we're going to close another parentheses for that n cap there. And so to plug our numbers in, we're going to have the 32 minus 35 for the numerator, divided by, you're going to do divided by, and then you're going to do a parentheses, and then a square root, parentheses, 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 12 minus 1, close parentheses, 2.1 squared plus, open parentheses, 15 minus 1, close parentheses, 1.8 squared, close parentheses to get that numerator done there, divided by, and then you've got your 12 plus 15 minus 2, close parentheses, to get that square root closed, and then we're going to do times the square root of, open parentheses, 1 over 12 plus 1 over 15, close parentheses, and then close parentheses for the whole thing. So let's take a look at our calculator. Open parentheses, 32 minus 35, close parentheses, divided by, open parentheses, second x squared, which is going to give us the square root, and then open parentheses, open parentheses, open parentheses, 12 minus 1, close parentheses, times your 2.1, which is your standard deviation. We got to square that. Square that. Plus parentheses 15 minus 1, close parentheses, 1.8 squared, close parentheses for the numerator, divided by, open parentheses for the degree of freedom, 12 plus 15 minus 2, close parentheses, and we're going to close parentheses for the whole square root, times the square root of, then we'll put that in parentheses, 1 divided by 12 plus 1 divided by 15, close parentheses, and then close parentheses for the whole thing, negative 3.997. We'll go with those 3 decimal places. And so let's go back here and try to fit it someplace. So we get our t is equal to negative 3.997. So that is going to be in the critical region. Therefore, we reject the null hypothesis, and the claim was not the null hypothesis. So therefore, there is enough evidence to support the manufacturer's claim that the wattage use of his 17-inch flat panel monitors is less than that is leading competitors.